Okay, hello everyone. It's my great pleasure to introduce our first speaker this afternoon, El Glaser. El's title is Seeing a Spectral Triple. So thank you very much, El, for agreeing to speak here. And please, floor is yours. Thank you.
Okay, great. Thank you very much. Thank you so much for inviting me. I've really enjoyed the conference so far, and I think the mini courses are really super helpful. Also, during the mini courses, I realized that maybe only part of the audience is that interested in the part about seeing spectral triples, but it was too late to figure out another talk, so I hope you'll indulge. So my talk today is about some work that I've done together with Abel Stern, mostly, and about what I'm doing with it now. The work with sorry, I forgot to write the reference on the slide first. So now there's the reference. So what I'm going to talk about today is work with spectral triples. So first, I'll give a quick reminder on spectral triples. I know John Barrett already did a very good introduction of those, but I think maybe not everyone was there for that, so I thought I'd give a quick refresh. And then I'll talk about how I'm trying to make a picture out of a spectral triple. But we know that the spectral triple contains the geometric information, but I'm not trying. I have an algorithm to take a spectral triple with finite matrices and make a picture out of that. And in doing that, I realized that I need some better examples than just spheres. So I played a bit with something that I call the deformed fuzzy sphere, and I figured out the eigenvalues and thought I'd share them because I'm kind of happy about it. So, well, as John already said, we have a spectral triple. What is a spectral triple? A spectral triple consists of three things. The three things are an algebra a Hilbert space H, and a Dirac operator D. Depending on what you want to do, you can also add to the spectral triple you can add to the spectral triple real structure J and a chirality gamma, but I'm not doing that at this point. That happens next slide. So what you need in your spectral triple is that your algebra A needs to have a faithful action on the Hilbert space. So you need some kind of representation with, for an element A and a vector in the Hilbert space, so that rho of A acts on the vector. You actually don't only need a faithful action, a representation, but also your Hilbert space should be a bimodule over the algebra. So you should have a right action to your algebra and a left action. And then, and the last thing that you need is that your Dirac operator should fulfill the first order condition. What the first order condition says is that the Dirac operator with an I'll write AR for right acting, commutes with another element left acting. So what that tells you is that your Dirac operator can have left acting parts and it can have right acting parts, but it can't have a part that is left acting and right acting at the same time. And with this spectral triple, if you're doing a continuous spectral triple with a commutative algebra, you can describe manifolds, and then you get the reconstruction theorem, and that is this work by Cons. But you can also do finite non-commutative spectral triples, and then you find that you get something very different. And one interesting thing to do with that is make it finite, which mostly leads to matrices. So we can do that special case of matrices. And that is where we get a fuzzy space. In the fuzzy space, we have some very particularly simple things. So our algebra for a fuzzy space is just the star algebra of the complex n by n matrices. And the Hilbert space, in this case, is just some PQ Clifford module tensored with the algebra. And so now, at this point, it makes sense to start also introducing the chirality and the real structure. And for doing so, we also should define the KO dimension. The KO dimension, S, is Q minus P mod 8. What the KO dimension tells us is just a bunch of signs. It tells us if the real structure and the chirality commute or anti-commute with the Dirac operator. And depending on the KO dimension, this will flip. And there's a periodicity of 8 there. It's a spinorial chessboard, if you will. Now, for this simple case of the fuzzy space, the chirality acting on an element of the Hilbert space, so I'll write that as V cross M. V is a part of the Clifford module, M is a matrix. Then the chirality is actually just the chirality on the Clifford module acting on the Clifford module part. And the matrix part is unchanged. And the real structure, J acting on an element of our Hilbert space, will do charge conjugation on the Clifford module and complex conjugation on the matrix. The interesting thing is that if we have a real structure, we can actually define a right action of our algebra from a left-acting element by just taking the complex conjugate of the left-acting element and then bracketing it in the real structure. So this is the mathematical structure of a matrix spectral triples. I haven't talked yet about the Dirac operator, because the Dirac operator is where this becomes really interesting. The Dirac operator has to satisfy a whole bunch of conditions. The first condition of the Dirac operator is that it's self-adjoint. Easy enough. The Dirac operator and the chirality need to commute or anti-commute, where this is again dependent on the KO dimension. The same is true for the real structure. Again, commutes or anti-commutes dependent on S. And then lastly, we have the first order condition. Now, if we take into account all of this information about the Dirac operator and put that together with what we know about how the chirality and the real structure act, we find that actually the allowed Dirac operators for a given A and H, for a given M and C, are tightly constrained. And John gave a few examples in his talk. I'm going to write just the most general version here. So any Dirac operator will consist of some product of gamma matrices. So this is a sum over all possible products of gamma matrices, and with each possible independent product of gamma matrices then arises a matrix K, and the matrix K and its complex conjugate, one is multiplied from the left, the other from the right, and epsilon is again a sign plus minus 1. If it's plus or minus 1 is again dependent on the KO dimension. Now, what this does for us is that now our Dirac operator basically just consists of a set of matrices. So all of the dynamic information in the Dirac operator, yeah?
So can I ask a question? Yeah. So Ki and omega I are independent of each other. I mean, completely. You're saying?
Yes. Yes.
I see. Okay.
So omega I is some product of gamma matrices, and each product of gamma matrices has one of these Ki associated with it.
Oh, I see. So you perhaps you choose Ki first and then omega I from maybe or something like that.
No, I can do a simple example.
Okay, very good. Thank you.
So if I do the Dirac operator, so let's do the example I have written down here is the 1-3 geometry. So what I get is that, so the 1-3 geometry has 3 gamma matrices, 4 gamma matrices, gamma 0, gamma 1, gamma 2, gamma 3. Gamma 0 is the one with a different sign than the other 3. Now, if you're taking these products, you need to take even or odd products, always so that the self-adjoint condition remains true. And what you get is that gamma 0, gamma j, gamma k, acting on the Clifford module part, cross some anti-Hermitian matrix, which I have now kind of tellingly called LJK. If we were to do a fuzzy sphere, LJK would become the algebra generators for the fuzzy sphere,
Yes.
the SZ2.
Thank you.
And then you get more terms, gamma 1, gamma 2, gamma 3, which has acting on V plus an anti-commutator of some H. And then you get some more terms. So all possible products of gamma matrices will appear in the sum. And then with each of the possible products of gamma matrices, you get a different matrix. And this matrix has to be Hermitian or anti-Hermitian, and will either be commuting or anti-commuting, will be in a commutator or in an anti-commutator with the matrix part. So, and that's just because that is the only structure that is allowed. Now, if you are thinking about, say, doing a path integral over these finite geometries, so we want to calculate some observable of these geometries from a path integral, what we would need to do is, I should write carefully because my f and my integral sign look similar. So we would integrate over this function of the Dirac operator, e to the minus some action of the Dirac, and then integrate over d, and then just normalizing with that basically. So with some measure over the Dirac operator, and this way we could calculate observables in this theory of fluctuating geometries. Now we have the question of what is how do we do this measure about the Dirac operator? And we can put in what we know about the Dirac operator there. And if we do that, what we find is that, well, we have a function of the Dirac operator, but the Dirac operator is a function of our matrices Ki. And the same is true for the action. The action is now actually just a function of these matrices. And we can then integrate over these matrices. So we have here a product over the matrices, and again, normalized by that. So what we have done is we've got the Dirac operator, which to satisfy real structure and chirality and first order condition and all of that has to have a lot of internal structure. And we've gotten rid of all of that extra structure by parameterizing it smartly. And now we can just integrate over these matrices. And that is the point where we get a multi-matrix model. Basically, our action in terms of the KI turns into this into traces and multi-traces. So well, normally at this point of the talk, I would start talking about the computer simulations of these multi-matrix models. But the last time I tried doing that and handwriting the talk, I did not get to talk about visualizations at all. So today I'm gonna leave this on the cutting room floor. Also because I know there's a lot of other talks that are going to talk about these Dirac ensembles still coming up in the conference, and I'm really excited to see what everyone else has been doing. So I think Carlos, Nathan, and Hans are going to be talking about these ensembles a bit more, and I think all of them are actually talking about analytic methods to solve it and using topological recursion and such. But I'm not that good at the analytic parts. I really enjoy doing the computer simulations. And what then happened in my computer simulations is that, cool, I get numbers, but how do I know what those numbers actually mean? I mean, I can get an average spectral triple out of what I've done in my simulations, but now I have some kind of spectral triple. What tells me what geometry the spectral triple that I have actually is? And that is the question that I'm trying to answer with what I've done next, which is making a picture of a spectral triple. So to make this picture, this is the work with Abel Stern, the reference I wrote on the first slide. We started out with, well, actually, when you have a spectral triple, you can recover geometry, as in you can recover the distance between states using the con distance measure. The con distance measure is the distance between states omega 1 and omega 2 is given as the supremum over all algebra elements for state omega 1 acting on the algebra element minus state omega 2 acting on the algebra element, under the condition that all algebra elements that show up in the supremum have a commutator with a Dirac operator that is less than 1. If we want to think about this in the continuum, we have the space of functions. And now the functions which have commutator 1 or less with the Dirac, the commutator 1 with the Dirac would just be the linear function. And you can see how if you have two elements, you can get their distance from the linear function there. So that is kind of the motivation, if we're going back to that. But we can write this down in general. Now, our idea was fairly simple. If we can find states on our Hilbert space that behave like points, and we can calculate using this distance formula the distance between these points, then there are computer algorithms that exist and that we don't even need to implement anymore. We can just plug them out of the libraries that will embed this set of distances and give us a picture of what we've created. Now, the tricky part of all of this is, of course, we need states. What are good states to do this with? And what we agreed on was that the states should be localized in some way. So obviously states in the Hilbert space can mean a lot of things, but localized or of a small dispersion are states that we think should converge towards points. in my work with Abel Stern, we actually proved that analytically for states that are in truncated spectral triples. Now, a truncated spectral triple or is an operator system spectral triple, as it's been, if you're going mathematically correct. But basically what it's doing is you take a spectral triple and you discard everything that has eigenvalues in the Dirac operator larger than something. So you're taking a cutoff, you're giving a maximum value that you want to see. But I'm sure that I know that it also works when you're not doing truncated spectral triple, but finite spectral triples, because I've made the pictures. I have an idea how I should do the proof, but I haven't actually found the time to sit down and do it yet. But I think based on Riefel's work, that should work out. Now, we should find the localized states, and then we can use the distances between the states to embed our states into the geometry. Now, if we want to do this, we of course need to figure out if we want to do this numerically, how do we parameterize all possible algebra elements? What do we look at that? And what states are a good idea? Now, for the what states are a good idea? So first for the algebra elements. Now, if we want to do the algebra elements, okay, I'm getting a warning that my internet connection is unstable. Can you still hear me?
Yes, I can.
Okay, good. Then, sorry. My internet has been acting up all day today, so I was a bit nervous, but so far, fingers crossed. Sorry. Back to algebra elements. Now, in general, we can always oh God. I'm sorry, my tablet has my tablet was glitching. In general, the algebra elements can be written as a linear combination of some basis elements. And then we just need to figure out the basis of algebra elements that is best. We can then just decide what are the best algebra elements. In the truncated case, we take the truncated spherical harmonics. That's just writing down a projection operator. That's fairly simple. In the fuzzy space case, I have two different options. Both work, one much better than the other. For finite, the easiest option is just to say I'll take all of the matrices that only have one non-zero element. That will definitely give me some kind of basis of the algebra that my computer can work with. It's going to be hugely redundant. It's going to be a lot of matrices, but these are definitely matrices that my computer will be happy enough to optimize over, and I can work with that. So I call that the naive implementation. What actually turns out much, much better is I can take the powers of the matrices that I had in my Dirac operator. Actually, all of the information that's relevant are is how my algebra elements interact with the Dirac operator. So I can just take all linearly independent powers of the matrices that show up in my Dirac operator. And both of them work. The naive one not as well. It's slower and it requires much more calculation. This powers works much, much easier and better. As an example, for the if I'm making a picture of a fuzzy sphere, this is just all possible powers of the angular momentum generators. And once I've generalized the parameterized my algebra, I can then do optimization of the. I can do my calculate the distance by minimizing under the condition that so I can just use that it's a linear combination and pull it apart to calculate it. So that works rather well. The much bigger problem is when we're talking about the dispersion. So how would we write the dispersion for these states? Now, if we want to write a dispersion purely in terms of the algebraic data, then that dispersion is the supremum over algebra elements of inner product of the state with itself, but with A star A acted upon, minus the absolute value of the state with A acted upon squared. So this acts like a dispersion. And again, we have to take the condition that the norm of the Dirac operator and A is smaller or equal than 1. Now, I can do that on my computer, I would think. No, wait, sorry. I can't do that on my computer. It's rather easy to write down, and writing it down, it looks nice. But if I'm doing it on the computer, I realize that there's 2 big problems. The first is that this is a non-convex double optimization. If I'm trying to find a state, well, if I have my state omega and I try to find a dispersion, I'm fine. That works. But if I'm trying to find a state omega with a small dispersion, that means that I'm varying omega, and then every time I need to optimize over all A. And this leads to what's called a non-convex double optimization problem, which just is not easy to implement. Because you have 2 optimization problems that need to that are dependent on each other, and there's no good way to say that you actually find the right answer if you're just doing that. The next problem is actually much easier, and we can solve that. The problem here is that our state's omega, if we're just optimizing by finding the smallest possible omega, nothing guarantees us that these states are actually distributed equally. In principle, our code might just spit out the same state over and over and over again, if that is the absolute smallest dispersion state. That's not good either. So we need to somehow force the states to be distributed across our geometry. Now, the solution that we found for the truncated geometries is to use the embedding maps YI. So these are actually just maps from the algebra to coordinates that you find in the case of truncated. Because if you have a truncated spectral triple, then that is a spectral triple where you, well, ideally you know the geometry, and then you can get these embedding maps because you are coming from the continuum. That obviously doesn't work so well for the finite spectral triples or fuzzy spaces. Interestingly enough, for the fuzzy spaces, you can use as embedding, well, not embedding maps, but it works well if you're just taking the angular momentum generators for this fuzzy sphere and also for the deformed fuzzy sphere. I'm still having a bit of trouble with the fuzzy torus, but I think that this has to do with another point of the algorithm where I need to find a distance. And I think the change in topology actually throws off one of the optimization algorithms that I'm just using. So, but we can just put in the angular momentum generators, or in a general matrix, we would just use, for a general matrix geometry, we would just use the Ki again, and that should work. The second solution is actually much easier. We don't want to find the same state over and over again. Okay, so we add a repulsive potential. We add in something that if we have two states and they're close together, they get pushed apart. And that is really just some constant and then so just some constant and then divided by the distance between two states. And if we do that, it works relatively well. And in fact, it's not actually all that dependent on the exact constant. So here are a few pictures that I made to check how it works. So without the constant, you can see here we find the same state over and over again. So this blue area is actually a sphere. It's just projected down into 2D. And you see that this is almost the same point. It's very much at the tip of the sphere somewhere. And then we need to add only, if we add an extremely small value, it gets better, but it's still not good. But then even moderately small or really large, the difference is not that large anymore. So the exact value of our repulsive term is not that important. Just adding a repulsive term means our states start being evenly distributed. Now, I've made plots of these states that makes them look as if they are points. That is not actually true. In actuality, these states have a non-zero dispersion, so they have a bit of a size. And
Oh, sorry, there is a question in the chat. El, do you want to? So.
No, the distance in the repulsive potential term is actually the distance for. Wait, sorry, no. Very good point. Ideally, the distance in the repulsive potential would be the const distance again. However, then we run into the same problem because we're trying to minimize omega. We try to minimize our dispersion, and if we're minimizing our dispersion, we have to also minimize the distance again. So we again have two optimization problems that are running together. So what we actually end up doing is we use a proxy for the distance. And basically what we do is we use, for the proxy distance, we use the embedding maps again, which is fine because we need something that is good enough. It doesn't have to be exact. We just want them to not be allowed to be the same, and the proxy is good enough to do that for us. So, did that answer the question, Michael? Good. So I've jumped a little bit just because I wanted to show the dispersion. I was saying in the plot before, we showed how the states are distributed. this shows how the dispersion actually changes. This is for truncated geometries. I'm switching a little bit between the two pictures just because the nice analytic work is done for the truncated case. For the finite case, it's not quite there yet. I'm hoping to finish it by the end of the summer, but as summer gets shorter, I'm less optimistic. But we see that if we cut off, so that the largest eigenvalue is 4, we have a fairly large bump. But then as the eigenvalue gets larger, our bump gets much smaller and sharper peaked. So it's doing what we would expect from such a state, what we'd expect our geometry, our dispersion to do. Now, jumping back, in the truncated case, we can actually prove that it works. What we have to prove is that states are points. So the proof itself is rather technical, but basically we're showing that for each state, there's a barycenter, and around that barycenter, the state is localized. So basically for each state, we can define one point that is the barycenter, which is the center point of the state, and the state is localized around that. And in the limit of an infinitely large truncation, so in the limit in which we get to the continuum, this state will become arbitrarily close to the barycenter. So any part of the state that is any part of the state that is far from the barycenter will become arbitrarily small. So we need to show that states are points. That is one half of it. The second half is then points are states. So that for each point in our geometry, we can find a state that has its barycenter arbitrarily close to that. So, and I do have a detailed version of the proof if anyone is really interested, but I think I'll skip over that. And if you want to come back to it, we can do that in the question time, maybe. I hope I will have some time for question. So we've already looked at the dispersion. I'm gonna skip over. So now we know how to calculate the dispersion of a state, and we know how to calculate the distance between states. And then our algorithm is actually fairly simple. We just start out with some state that minimizes the dispersion and add that as our first state. And then we keep adding more states. Of course, because we are doing this numerically, in principle, we could keep adding arbitrarily many states. If we don't add a termination condition, the computer will just find states that keep adding. What we do to add as a termination condition is that the sum of the square roots of the dispersion should be smaller than some numerical constant times the distance. This numerical constant in the end we can put as, I think we just put it as 1, and that's a good approximation. But basically we're saying as soon as the dispersion of the states is so large that they would overlap, we have enough states. So once the states are all touching, we should stop generating more states. And then we just keep going. We locally find a state that minimizes our dispersion with the repulsion term. And then we actually calculate. So once we found a state that minimizes our dispersion and the repulsion term, we add it to our set of states, and then we calculate the condistance between the states. So find a new state that minimizes dispersion, and then calculate the exact con distance. And that gives us then, in the end, a distance matrix, which is really just a matrix that is 0 along the diagonal. And then it just says how far apart the different states are from each other. And then with that matrix, we can go and use the embedding algorithm. The embedding algorithm we use is called Markov, which is scaling by majorizing a complicated function. That's what the algorithm is called. And basically all that it does is it starts assigning coordinates to each point, and then it wiggles the coordinates until the different points actually have the right distances between them. And once we have done that, we've assigned coordinates to the points, we can then make a pretty 3D plot of the points, such as this of a truncated sphere. So that's a nice plot of a truncated sphere. If I make a plot of a fuzzy sphere, I get basically the same picture. That's great. But if I want to be sure that this algorithm works, and eventually I would like to take this algorithm and actually throw in some of the fuzzy spaces that my computer simulations and the computer simulations of Mauro that John had mentioned have generated. Well, if I want to look at them, I better make sure that the algorithm does what it should. I am trying to figure out the fuzzy torus, but I'm having trouble, so I wanted something else that works and that might be a bit easier, which is why I thought back of the deformed fuzzy sphere. So the deformed fuzzy sphere is a spectral triple with the algebra are A, M, and C. The Hilbert space is D4 cross M and C. A nice basis for these, in this case, are actually the irreducible representations of SU2. And then the Dirac operator is gamma 0 plus gamma 0, gamma 1, gamma 2. Gamma 3. So where the L, J, K are generators of SO3. Now, if it's like this, it's the fuzzy sphere. Now, if I want to make it a deformed fuzzy sphere, then I can just add some constants here. Just rescale different directions, and one would hope that that gives me some kind of an ellipsoid. The question is, does it really? Or if not, what does it do? How should this look? And so that's what I then thought, okay, I can play with that. This is simple enough that I know my algorithm will work well, but it's also simple enough that I can do some analytic work to understand what is happening. And the first thing I did is just set C1, C2, C3 as only C1, 1. So I only deform in one direction. It actually doesn't matter in which of the 3 directions I deform, the result will look the same. And if I do that, I can actually even exactly calculate the eigenvalues that I get in this case. So again, this is something that I'm fairly sure it's correct. I've done some parts of it with Mathematica, and then I figured out the pattern. Writing out the proofs that my pattern is correct is waiting for me for after the conference. But what I find is that the eigenvalues have a simple pattern. So if I increase my matrix size, from n minus 1 to n, then I get a set of eigenvalues. And the new eigenvalues that I get is I'll get each of the eigenvalues twice. So I get plus minus 1 plus n minus 1 times my constant c. So that is the simple one. And then I get n minus 1 sets of eigenvalues, which are in the form of a square root. And I can label them with some k in positive whole numbers with k smaller or equal than n minus 1. And those eigenvalues have the form of plus minus 1 plus a over 2 plus minus the square root function of k and n plus 2k minus 1 over 2 a to the square. And this function of k is just n minus 1 minus k minus 1. And okay, I can write that down and yeah. So where it gets fun is when I'm plotting it and I can look at that. So this is the plot for n equals 3. And these are only the positive eigenvalues for n equals 3. If I added positive and negative eigenvalues, my plot would get a bit busy. You can see this is, sorry, I called it A here, it should be called C, but so you can see this is the plot of C equal 1, which is the sphere where we get the high multiplicity of the eigenvalues as is typical for the sphere. And then we can look at the eigenvalues overall. And yeah. Good. Maybe more interesting than the eigenvalues is what happens when I'm using my embedding algorithm on these deformed fuzzy spheres. And that's what is happening in this point. I realized I have switched my notation a couple of times along the way. So this should be called C. And so C equal 1 is the sphere, and we see here the points are the embedding is very spherical. If we add just a little bit of deformation, we don't see much of a change. But even here, with the modest deformation, we can kind of see that it's looking more like an ellipsoid. And then if we increase the deformation even more, we actually see it becomes almost a line. So if we deform one direction enough, it basically, well, what happens is actually it's not one direction that disappears, but two directions. So we're only left with one with a kind of line here. Good. We can then look at how good is this embedding actually, and to check how good the embedding is I just look at how close are the distances between the states to what they should be by calculating the correlation between them. And you can see the smallest point on my plot is at 0.9975. So that is almost perfect correlation. So the embedding into 3 dimensions is working very well, which is actually interesting because when I'm doing the embedding, I have to tell my computer, okay, embed this into 3-dimensional space. I could just as well embed it into 2 dimensions or into 4 dimensions. And other dimensions might work better or worse. I think this is actually one of the points where the torus goes wrong. I'm trying to embed into 2 dimensions because embedding in 4 dimensions just gets very hard to plot, and I can't embed a flat torus in 3 dimensions. Well, I can't embed a flat 2 torus in 3 dimensions. But sorry, I'm getting sidetracked. So this works very well, and it's telling me that my embedding is good. So great. That means I probably should put it onto the other geometries. Okay. Now I'm already at the end of my talk, so I can just summarize what I've talked about. I talked about exploring spectral triples using computer simulations, or well, today I mostly talked about finite spectral triples and the definitions of them, and how you get a finite multimatrix model from finite spectral triples. And then I showed how we can get a picture of a spectral triple using the Kohn distance function. And for the future, I want to do the fuzzy torus, but I still have to figure out that problem with the topology, I think. I think there's more analytic results to be had on the deformed fuzzy sphere. And understanding the deformed fuzzy sphere is interesting because this will be a fuzzy space where we can understand the geometry, but also change the fuzzy space. We have a parameter to dial around with. And my hope is that maybe we can create bespoke fuzzy spaces. Maybe at some point I can not only do a fuzzy egg or something, but maybe I can say, oh, I want to draw a little fuzzy heart and see what that does or something. Okay, so yeah. Thank you all for your attention. And
Thank you very much, Elle. Thanks. Let's thank Elle again.
I'm gonna stop screen sharing just because my computer refuses to show me your picture when I'm sharing the screen, and it's a bit eerie to just talk into nothingness. I can turn the screen share back on if there are questions then, but
Okay.
I want to see
Great.
you.
Yeah. So very good. Thanks. Yeah. So are there any questions or comments? Yes. Look. Yeah, please. Do you want to get this? Yes.
When we're looking at the deformed fuzzy sphere, it seemed like you got this squeezing effect, but the squeezing effect sort of rotated. Do you know why that is?
That has no meaning. Just starting with my, I just pick a random point, and that is the one that is fixed, and then I do the embedding around that. Now the random point can be any of the points, but it will define the direction.
Right.
So
okay, thanks.
The rotation has it's free the same just can't fix it. I could fix it afterwards in my plot, but yeah.
Right. Thanks.
Other questions or comments from the audience here? Maybe I ask one question myself. So you showed some pictures in this, like, can you hear me? Yeah. Oh,
yes,
now.
I can hear you.
Okay, yeah. So you showed these pictures of this sort of spheres, and you got it by some optimization techniques. I just wanted to make sure those individual points, in some cases, they were like on the same line when I think n was equal to 100 or something. They were more or less located on the same line. What those points reflect? They correspond to different Dirac operators or what?
But no, these are so okay. So you're talking about each of the points.
Yes,
is
exactly.
A state
Yeah.
on my Hilbert space that I know.
Yeah.
So each of these pictures is a figure for which the constant C information is set to some. So each of the points is a state until space. I calculated the distance between these states using the same Dirac operator.
I see.
That
Ah,
it's the states to have minimal dispersion under the same Dirac operator.
okay, I see. Okay, very good. Are there any other questions from the Zoom audience? Okay, looks like there is nothing. So let's thank Elle again for a very nice talk. Thank you.
Thank you.
So we will have half an hour break and then we start at 4, it seems. No? Okay. Thanks.
Okay.